Every year, the Earth undergoes a massive redistribution of life. Millions of animals cross continents and oceans to chase seasonal food supplies and secure safe breeding grounds. Gray whales handle these vast distances with sheer physical mass. They travel roughly 12,000 miles round trip, from the icy waters of Alaska down to the warm coast of Baja, Mexico. Even though a gray whale is swimming up to 185 kilometers a day, it is traveling through its own food supply. It can stop, rest, and consume krill whenever it needs to refuel. These massive journeys require high endurance, but they obey the standard rules of biology. As long as an animal can pull over to rest and eat, the distance is just a matter of time. Curious, slightly hushed. The Pacific golden plover is a bird roughly the size of a common dove. It weighs about 130 grams, and its feathers are not waterproof, meaning it absolutely cannot swim.
Yet to survive the winter, this bird flies from its breeding grounds in Alaska to the islands of Hawaii. That is a 4,500-kilometer continuous flight over the open Pacific Ocean. Because it cannot land on the water, the plover must remain airborne for 88 consecutive hours. To maintain altitude, it has to flap its wings 250,000 times without a single break. To prepare for this, the plover spends weeks in Alaska gorging on insects. It adds exactly 70 grams of fat to its 130-gram frame. That fat is the only fuel it has for the entire trip. We know that a golden plover burns 0.6% of its current body weight in energy for every hour of flight. This graph plots that exact burn rate against the distance to Hawaii. If you run the 88-hour timeline, the bird's 70-gram fat supply drops to zero while it is still 500 miles away from the islands. According to its own baseline metabolism, the bird is mathematically guaranteed to run out of energy and drown. To survive, it has to find a way to manipulate the laws of bioenergetics. The first thing the plover does is lock into a biological cruise control. It maintains a strict, constant speed of exactly 51 kilometers per hour. This speed is highly deliberate. If the bird flies slower, it wastes energy fighting induced drag, which is the aerodynamic resistance created as a byproduct of generating lift. If it flies faster, it burns fuel at an exponential rate just fighting air resistance. However, even at a perfectly optimized 51 kilometers per hour, the math still shows a solitary bird will run out of gas and crash. This diagram shows the solution. Plovers fly in a strict V formation. By positioning themselves precisely in the wake of the bird ahead of them, the flock drafts off the leader. They rotate the lead position, and the resulting drag reduction saves the entire flock exactly 23% of their total energy. As this diagram updates, you can see how that 23% savings changes the math. The hourly fuel burn rate drops to 0.462%. The bird reaches Hawaii with 6.8 grams of fat left over to handle unexpected headwinds. The solitary bird is physically incapable of the journey. The flock survives by executing a highly calculated aerodynamic strategy.
Having enough fuel is only half the equation. Hawaii is a microscopic target in the Central Pacific. A heading error of just 2 or 3 degrees at the start of the journey means the flock will miss the islands entirely, exhausting their fuel over open water. To hit the target, the plover relies on multimodal sensory hardware to calculate a great circle trajectory, which is the absolute shortest possible path across the spherical surface of the Earth. First, the birds use magnetoreception. Their retinas contain cryptochrome proteins, specialized light-sensitive molecules that allow them to actually see the Earth's magnetic field lines and lock onto a compass heading. Second, they actively compensate for wind drift. If a crosswind pushes them sideways, they don't just point their beaks toward Hawaii. They calculate the lateral force of the wind in real time and angle their bodies into it, ensuring their actual path over the ocean remains a perfectly straight line. The adults of the flock actually depart Alaska several weeks early. When the newly hatched chicks finally have enough fat to fly, their parents are already in Hawaii. This means juvenile plovers execute an 88-hour, 4,500-kilometer flight across a featureless ocean entirely by themselves, without a guide. They do not learn this route. The destination coordinates, the magnetic compass, and the math for wind drift are hard-coded directly into their DNA. The migration of the Pacific golden plover is an exercise in extreme metabolic engineering. It works because 3 highly specific variables align perfectly: the 70-gram fat payload, the exact 23% aerodynamic savings of the V formation, and the genetic navigation system keeping them on the absolute shortest path. If any one of those variables shifts, the bioenergetic equation collapses and the birds drop into the ocean. There is virtually zero margin of error. This level of natural optimization allows the plover to achieve a mathematically impossible feat, but it also renders the species incredibly fragile. That fragility is being exposed by anthropogenic climate change, which is creating a phenological mismatch in the Arctic. A mismatch occurs when the timing of seasonal biological events falls completely out of sync. Warmer temperatures cause the spring thaw to happen earlier. The insects hatch early, complete their life cycle, and die off before the plover chicks are physically developed enough to feed on them. This chart tracks that divergence. The red gap is the missed food window. Without those insects, the chicks cannot accumulate the required 70 grams of fat, guaranteeing they will fail their first southward migration. Add to this the physical risks of newly constructed wind turbines placed directly across their historical flight corridors, which force the flocks to waste precious energy taking evasive maneuvers. The survival of the golden plover relies on a perfectly balanced zero-tolerance equation. When we rapidly alter their environment, we introduce variables that their biology simply does not have the fuel to solve.